It's now 10 o'clock here, as you can see. And yeah, let's start this. So my name is Arif. I was one of the early beta user from SIMBA. So one thing to find about my one thing I contribute to SIMBA is you can find in the example on the SIMBA, you can see the SR buck converter. That one was made in C code. And as you can see from that example, and basically I'm a big fan of C code. I always use C code for all of my simulation. And honestly, I do not really understand how to design controller with the blocks. So anyway, let's move on. So my presentation is about the bidirectional interleaved totem pole inverter. Okay. And then if you want to find out more about me, you can see my information in my LinkedIn or in my GitHub to find things that I share publicly. Okay. So short outline, we have the introduction, the PWM models, noise modeling, and then the control structure and schematic and the waveforms. Okay. Okay, sorry. Oh, sorry, the title is wrong here. So this should be an introduction. So basically, the presentation will focus on the method that I use to close the gap between the simulation and the real world phenomenon. So some of the things that I found that was interesting when I was making something here was, number one is the accurate PWM model. So basically, one thing that often catch people when they are working on the totem pole control is how the output behave around the zero crossing. So I find that making sure that we can simulate how the PWM is handled from the MCU inside the simulation environment is particularly important. The other thing is how sensor noise can also cause some issue. And unfortunately, as we all know here, basically every simulation is ideal, so you do not really see simulation. So yeah, I also show how the noise is being modeled. And then last one is for this particular case study of same as the title. So we are going to use the totem pole inverter with interleaving. All right, so number one is for the accurate PWM model, basically the idea. Now, the first thing that I would like to point out is PWM is not exactly a comparator. So in the world, PWM is only defined when the counter is equal to the CMP. Only at this time, not like the way we normally generate PWM with a larger, greater than or smaller than. And then the behavior of the output is defined also based on the slope where the counter is currently being at. And then the other thing is what the other one that also a lot of people often miss is CMP update is actually mostly synced with the counter when the counter is equal to 0. Oh, one thing I have to note is that the terminology here that I use is actually reflecting the MCU that I often use the most, which is from the Texas Instrument. So if you are not familiar, but then yeah, my apology. And then yeah, so the way we need to do is for this kind of PWM simulation, the way I do is basically I can compute the exact time when the PWM output should have the transition. So when the output should change from low to high and high to low, and then also to generate the trigger for the ADC sampling on the controller sampling. And because in my particular case, I use oversampling by 4 times, so I have to generate the sampling at all of these 4 different conditions. Okay, and the way I did is basically I'm making the PWM without any single carrier being actually generated. So later when you see my schematic, you do not see any triangle being generated ever. And there is no actual comparator there in the schematic. And instead, what I did is all of the PWM is handled by a C block, and this is basically the library that I'm using. Okay, so the way the PWM handler works is basically number one, by calculating the occurrence when the output should change from 1 to 0 and 0 to 1. And then if there is a change happen, then the next thing that I will call is a dead time handler. So because the output between high side and the low side will have some kind of dead time. And then the other part here is to call for the interrupt trigger or for the ADC sampling. And then the way I can perform all of this PWM handling is by leveraging the function that is made inside the SIMBA, which is the next discontinue event. So basically what I can do is I can just tell SIMBA to directly hit the estimated time when the PWM switching should happen based on this calculation here. Okay, and then okay, so this now I will show you what will happen when we are using the standard PWM, and when at the same time we need to handle the zero crossing. So this is a single phase interleaved totem pole inverter, or a PFC. And then for this one, I just use a basic standard. And what will happen is in one of the zero crossing, you will see massive spike here. And the cause of this massive spike is because the switching of particularly here, the low frequency PWM is actually not synchronized with the rest of the high frequency PWM, even though when we are looking at the duty cycle assignment here, we are having the transition at the exact same time. And because of this, and of course, when we have large voltage, large time discrepancy here, then we will have large voltage across the inductor, and thus the large current spike here. Okay. And yeah, this behavior, you can also observe this on the real hardware when you make it. And anyway, my solution is actually not just using the firmware solution, like what is generally suggested on the paper, but I also have some kind of hardware solution. But yeah, the detail is, yeah, just keep the detail as a magic. But by the way, what I managed to perform is basically I can make sure that the transition now is clear at around the zero crossing. Okay, and then next there is a noise characterization and the modeling generation. So basically, I have one kind of Hall effect current sensor. The current sensor has a 40 amp current rating. And then, as you can see here, the noise peak-to-peak magnitude is pretty big, because if the 1 amp is represented by 33.3 millivolt, but as you can see, the noise peak-to-peak is actually around 40 plus minus 40 amp, and actually almost plus minus 50 amp. So the noise peak-to-peak amplitude is very big. And yeah, this is the reality of the Hall effect sensor, which is pretty noisy. And so the way I can mimic the noise inside the simulation environment is by first performing the characterization. And what I did is I import this data into Octave or MATLAB, and then I can make the power spectral density plot here. So this is not a standard FFT. This is a power spectral density. So the idea is for the noise density, the measurement is also normalized by the sampling rate. So, because otherwise the noise that is shown in the chart will be heavily dependent on the sampling rate. And then the other thing that I do is try to plot the distribution of the noise, and turn out that the distribution it's not exactly perfectly matched with the Gaussian, because the peak is kind of very high here. But anyway, the shoulder looks pretty much similar. So what I did is then because I see, okay, I assume that this is one looks pretty much like a Gaussian noise. So what I can do next is just generate a random noise in the MATLAB and then adjust the standard deviation. And then I can observe in the time domain, it looks pretty much similar. And then in the spectrum density and then the histogram, it also looks pretty much similar or reasonable. Okay. And then to make sure that the noise generation doesn't bog down the simulation speed, I only generate the noise at 4 times of the switching frequency, which is equal to the ADC sampling rate. Okay, and then for the actual noise generation in the simulation, I'm using this method called Marsaglia Polar. So this method was developed by Professor Marsaglia, and yeah, we can see the algorithm here. So the idea is the algorithm will convert from the uniform random, where you can use directly in the C code by calling the rand function, and then yeah, use all this simple algorithm to convert it into Gaussian random. And then this is the overall control structure of the totem pole inverter. So as you can see here, we'll have the voltage reference, and then we will have the voltage controller with the gain scheduling. So when the error is small, then I can reduce the gain to improve the THD. When the error is large, then I can increase the controller gains for a short moment to bring down the output to regulate the voltage quickly as soon as possible. And then I can generate based from here, then I can actual grid voltage. And then from here, I can generate the AC current reference. And if I want, can also add the reactive current reference here. And for the actual current control, I'm using a proportional resonance control. And you can see here that there is actually another input for the PR controller and the notch filter, because actually, as you may understand, that the PR controller is kind of sensitive to the grid frequency. So I have to make the PR controller and the notch filter to be adjustable. So yeah, those two things has been done. And because so for my control design here, I take these two inductor current as one. So that's why the actual main current controller is using the sum of the two current. And then after that, I just make a small balancing algorithm control here using a PI controller to adjust slightly the duty cycle between the first leg and the second leg. And then after that, then the signal goes to the PWM logic with the data and gate driver, and yeah, we'll see the result after here. So yeah, so this is the overall simulation. As I mentioned before, all the PWM generation is made inside the C block, and then all the controller also in the C block. Normally, I put all of this in the same block, but yeah, for this time, I just decided to put them in separately because I think it might be slightly faster if I combine them. Okay, and then so because this is an inverter, so on the output here, I have a controlled current source where at the first part of the simulation, I will simulate when the current source here is actually sinking current from the DC bus. And on the second part of the simulation, we will see when the current source is actually sourcing current into the DC bus. And we will see what will happen on the circuit behavior. Okay. So yeah, here we can see the overall simulation result. So on the middle here, we see the output voltage in the red color. And then on the top here, we can see the controller response. And then on the bottom here, we can see the individual current of each inductor. So what we can see here is, yeah, the PR controller response is actually diminishing over time, because as we understand that actually the response of the PR controller tends to be very small in the good cases, but when it's about the load transient, massive load transient, then yeah, we will need to make the correction. And then for the inductor current balancing output, it's mostly what we can see here is just noise. But what the good thing is, it can still make some small adjustment to ensure that the current in the two inductors are balanced. So now we can take a little bit of a zoom here. So in this one, we can see that at the steady state, so basically these two are at the steady state. The difference is on the one on the left is from 0.76 to 0.8 second, and the one on the right is from 1.56 to 1.6 second. So what we can see here is, yeah, the PR controller response is pretty much well bounded with quite small correction needed. And then we can see that the zero crossing is handled properly. And yeah, everything looks mostly nice. And then the balancing algorithm is also pretty much only performing very minuscule response. And because in this simulation, I also add the noise. So you can see that the controller response is also not perfectly clean. Okay, so guess that's the end of my presentation. And the conclusion is learn C programming, even for hardware engineering. Because with the C programming, then the sky is the limit. You can have the highest motor accuracy with less headache when you are actually migrating from simulation to MCU. Okay, I guess I'm right on the clock.